Hello. Is my mic on? Yes, it is. All right, let's get started. Welcome to Day 8, Lecture 19. Today we're going to be continuing our discussion of hypothesis testing, and we're going to be talking about what we call error probabilities. I hope you're ready. So some announcements, which I have forgotten to write down. Let me just pull those up. Pull up my announcements. Nope. My announcements. OK, so homework 5 is released. We changed the due date, so that it's due Monday night instead of Friday night. OK, so if you did not want to do it before the midterm, it's not due on the day of the midterm. It's due instead the Monday afterward. However, the material on homework 5 will be tested on the midterm, so I suggest that you do it because it'll help you. It'll help you prepare for it. Monday, and that is because we're canceling office hours on Friday, so that we can grade your midterm faster. Okay, so no office hours on Friday, only office hours on Thursday, and the office hours on Thursday are moved to 367 Cori instead of the usual 258 Cori. There is a midterm on Friday. I hope you guys know that by now. Midterm on Friday, 10 to 12. We have reserved the data lab rooms for you to take your midterm in. We're going to be releasing a seating assignment hopefully by the end of today, so keep an eye out for an email on Piazza about that. Okay. But it will not be held here. You'll go to your respective room for the midterm so that you'll have better lighting, an actual table to write on, all of that good stuff. Lab on Wednesday and Thursday is midterm review. So you'll be going over practice problems with your TA and your lab assistants. Lecture on Thursday is midterm review as well. And tutoring is also midterm review. So all midterm review, the days leading up to the midterm, to try to get you guys up and ready, prepared for the midterm. Okay, so if you have not signed up for tutoring, I believe there are a lot of open spots. So please sign up because that's like a lot of good help you can get from MLR Tutor. All right, so lab, lecture, tutoring, all for midterm review Wednesday and Thursday this week. Any questions? Oops. All right, let's move on. Whoa, where's my button? Here it is. Okay, so last time, and it's not on. Last time, we ended class by talking about hypothesis testing, which is just a fancy word to describe the kind of the process that we've been doing for a couple of lectures now, right? So in the jury example, we did like a quote-unquote hypothesis test, although we did not run through the formal steps of conducting a hypothesis test. So I'm going to talk about the formal steps for conducting a hypothesis test now, and then we'll do an activity in class to try to show you what it's all about. Okay, so when we're conducting a hypothesis test, we start off with our hypotheses. Basically, we have two views of how the data were generated. So where does this data come at random, and I just got unlucky or lucky depending on how you want to look at it. So did my data come by random chance, which is a null hypothesis, or did something else happen, which is my alternative hypothesis? Once I define my two hypotheses, I select a test statistic, which is a measure of how different my sample is from a population. Okay. Finally, I simulate. So I simulate draws from the population to try to see what values of my test statistic are likely to occur by chance. So in the jury case, we had some distribution of ethnicities. We drew panels at random, and we said, OK, what's a TBD that's pretty likely to occur? So we got TBDs in like 0.05, 0.1. And it looked like our TBD, the TBD that we got in our original sample, our original panel, was like 0.18. 0.18 did not look like the rest of the TBDs. It did not look like it was drawn at random from the actual population. So we said, this panel looks suspicious. Okay. So we are approximating the sampling distribution of the test statistic, which is a theoretical distribution. So we can't calculate precisely the distribution of values of that statistic. But we can approximate it by drawing at random from the population. We're trying to do in a hypothesis test. Cool. So I would like all of you guys to pick a number between 1 and 100. Okay, so pick a number in your head. Hold on to that number. Okay, so that number is what I call your weirdness level. Okay, so the higher number you picked, the more weird you are. I'm sorry if you picked a high number. But my question is, So I also have a weirdness level. My weirdness is pretty high. So let's say my weirdness is like 85. Okay, so my weirdness is 85. I want to know whether my weirdness level was likely to have come from the classroom or not. Okay, so to be clear, my population in this case is you guys, the classroom. Okay, and the question is, did my weirdness level 85 come from this classroom? So could I have been one of you guys, the students? Okay, so my hypothesis is, the null hypothesis is, my weirdness was drawn from the population of data 8, I guess, to be more clear, the population of data 8 on this particular day in lecture. Okay, so there's like, let's say 50 of you guys. I was drawn at random from you guys. The alternative is that my weirdness level was not drawn from you guys. My test statistic, which is just a measure, again, a measure of the difference between me and you, is just weirdness, right? So the higher number is more weird. So if I have a weirdness of 100 and someone in the classroom has a weirdness of 1, then it's a pretty different weirdness level. Finally, the sampling distribution of my test statistic. In this case, I don't need to do anything special. I can just ask you guys what your weirdness level was. Okay, so how many of you guys chose a weirdness level of at least 1? Should be everyone. Okay. How many of you guys chose a weirdness level of at least 10? At least 10. Of at least 20, 30, 40, 50, 60, oh no, 70, I'm looking pretty weird. 70, 80, oh no, 85, 90, 100, okay. What did you pick in the back? 99, okay, pretty weird. Okay, so how many guys, so let me ask you, how many guys picked a weirdness level of 85 again? Let me ask. At least 85, I think there are three of us. 3 of us? Yeah, so there are 3 of us, right? So that means that if I looked at the classroom and picked one of you guys at random and I said my weirdness level is that number, so I picked at random from the classroom, let's say there are 50 students here. If I pick at random, the chance that I get at least 85 weirdness is 3, because there are 3 of you guys that raised your hand, 3 in 50. So the chance of me drawing my weirdness level 85 was about 0.06 or 6% chance. Okay, that is basically the heart of a hypothesis test. 0.06 chance is pretty low, right? So you can make a judgment call and say, oh, it seems likely or it seems unlikely that I was drawn from the classroom. We'll talk about those like judgment calls in a second. But I kind of want to give you guys a sense of what exactly is going on in a hypothesis test. I just have some question, which is, well, did I come from the classroom? And then I can ask the classroom, see the distribution, right? So there I looked at the distribution of weirdness levels in this classroom right now. The distribution of weirdness levels, and based on a distribution, I can say, if I had drawn at random from you guys, what is my probability? What is the probability of me getting 85, at least 85 as my weirdness level? Okay, so keep that example in your head, because we're going to move on to an actual example. Are there any questions about what I just did, first of all? Yes? Yeah, so the question was, so in this case, I said the population was you guys. And usually we work with samples, right? So in this case, since I have the whole population, I can actually compute that probability of drawing my weirdness exactly. So the probability of drawing at least 85 as my weirdness is exactly 6% in this case, because I know I just ask all of you guys to raise your hand. If I don't know everyone in my population, right? Let's say instead of asking just this classroom, let's say in the fall. So in the fall, data 8 will have, I think, about 700 or 800 students. I'm not going to ask every single one their weirdness level. Let's say I only ask 50 of them. If I ask 50 of them and then do the same thing, I might still get 6%, but it'll be an approximation of the population, right? So if you guys were not my whole population, but instead you guys were my sample, which is a normal case, my measurement of my probability is 6%, is only an approximation of the actual probability. We think that it's close, but it's not exactly there. Good question. So yes, it's true. So if you actually have access to the entire population, there is no need to do a hypothesis test. I can just calculate everything that I want exactly. If I have a sample, that's where you get some iffy stuff happening, but we can look at that iffy stuff by looking at how random chance behaves. All right, so let me go through one example. So Gregor Mendel was an Austrian monk, and he founded the modern field of genetics. Okay, so if you guys are familiar with this pea plants experiment and the colors and the heights of the pea plants, you're probably familiar with his work. Basically, he said, it seems like if I grow pea plants, I'll get purple and white pea plants in the ratio of 3 to 1. So for every white flower, I'm going to get purple. I'm going to get 3 purple flowers. Okay. So my question is, was his model correct or not? And my null hypothesis is that it is. So Mendel's model, in fact, does describe the world. If I grow pea plants at random-ish, right? If I grow pea plants at random, I'm going to get about 3 to 1 ratio of purple to white flowers. And my alternative hypothesis is that something else is happening. Okay. So what Mendel did was he actually grew a bunch of plants. And he said, oh, it looks like about 75% of these plants are purple. Okay, so maybe he got like 76, maybe he got 77. We'll take a look at his actual number in a second. But let's say he got 77% were purple. We can then ask the question, well, is that close enough to 75% that we can say that it was a 3 to 1 ratio? That is a question we're trying to answer with this hypothesis test. Okay, so null, alternative. Let's take a look at it. All right, so make that full screen. Here we go. So my null hypothesis is that I draw flowers in a 3 to 1 ratio, purple to white. So here I have an array with 3 purples and 1 white. Okay. What I'm going to do now is take a sample. So I can take a sample of these flowers. No, let's say I take a sample of size 10. If I take a sample of size 10, I expect that about 7 or 8 of those will be purple. Let's figure out how many of those were purple. So let's call this my sample. Okay. We expect that about 7 or 8 of them are purple. Let's take a look. So sample equals purple. So we have some trues and falses. Let's figure out how many trues there were. Count non-zero. There are 6. So not exactly 7 or 8, but pretty close. Okay. And what I'm going to do is divide this by the total number in my sample. So I say that 60% of my flowers are purple. Okay, so I get a proportion. And Mendel proposes that the proportion should be 0.75, right? And I'm asking the question, OK, what happens if I get something different? I need a measure of how different that proportion is from 0.75. So I'm going to subtract the 0.75 and say, OK, this is my test statistic. Like proportion. Okay. Now, what if I take another sample and I get more than 75% purple? So let's say, let me do this a couple times. Let's take a look. Looking for a lot of purples. OK, this is a lot of purples. So in this case, it looks like I only have 2 whites and 8 purples. So that means that this proportion should be higher than 0. What I'm trying to measure here, so in this test statistic, what I'm trying to measure here is a difference. So I'm trying to say, was this model correct at 0.75? Or was it not, right? So if his model was actually correct at 0.75, we expect that most of the results should appear around 0.75. But if his model was not correct, then we can expect results that are either higher than 0.75 or lower, right? If I had gotten all purple every single time, that would be pretty suspicious. If I had gotten no purples at all, that would also be pretty suspicious because his model would look like his model was incorrect, right? So I want my test statistic to be higher than my results are from his proposed model. In this case, my statistic results are lower and higher depending on how different it is. But if I take the absolute value, then my results will always go up the farther away I get from 0.75. So if I had gotten a sample with no purple flowers, meaning that the proportion of purple flowers is 0, my test statistic value would be 0.75 because I'm 0.75 away from the theoretical. On the other hand, if I had gotten all purple in my sample, then my test statistic value would be 0.25 because I'm 0.25 away. So that means that the higher my number is, the more different I am from what Mendel proposed. Okay. So I'm going to define that test statistic. So I'm going to call this proportion purple. Oops. And I'm going to say, just take that. And instead of dividing by 10 here, I'm going to take the length of my sample. So that way, even if my sample size changes, I'll always get the correct proportion. So there's that. And then, let me do that. Okay. And then I'm going to return the proportion purple. Okay. So if I had given it an array with only one purple flower, the value of my test statistic is 0.25, because it's 100% purple, which is 0.25 away from my proposed proportion, 0.75. If I only had one white flower instead, oops, white, then the value would be 0.75. Okay? So the higher it is, the more different it is. That's how I construct the test statistic in order to actually find out how different my results are from the theoretical. Any questions about that? Okay, so I've stated my null, I've stated my alternative, I've chosen my statistic, my measure of difference. Now let's actually take draws from the population and see what we get. Okay, so Mendel's actual result, I should have written it up here, but Mendel's observed proportion was, let's take a look. So he observed 705 flowers out of 929 flowers were purple. Okay. So he got a proportion of 0.758, 7.759, right? So that means that his actual observed statistic, we're going to calculate it in the same way that we did here, which is subtract the 0.75, and take the absolute value. And I'm going to show that. Okay. So he observed a test statistic of 0.009, which is pretty low. Okay. But how low is actually really low? The only way we can find out is by taking random draws from the population and taking a look at the results. Okay. So I have this, and he took 929 flowers. So total plants, 929. Okay. So that means that I want to sample 929 flowers. I want to take a bunch of those. So I'm going to take a random sample of my null under this sample. So I'm going to say 929 flowers go in the sample. So total plants. I have here 929 flowers, right? So I'm simulating growing another 929 flowers. And I'm going to take a look at the test statistic for that sample. Since I wrote that in a function, I don't have to copy and paste that code again. I can just call the function on my sample. And I get, oh, OK, this is 0.19. This was 0.0029. This was 0.005, right? So I have that. And so I want to repeat that. I write a for loop. Okay, so let's write repetitions. I can never spell that correctly. Let's take 5,000 draws. And let me save the stats in a sample stats array. Okay, so I have my array. So I have my for loop. Repetitions. Calculate my test statistic, and then save that in my sample stat. So sample stat equals that. And then sample stats equals np.append sample stats with my stat. Let me call this stat, because that's more simple. Stat. Okay. Now I have a bunch of these differences from proportion, differences from 0.75. And I want to look at the distribution of that to see whether Mendel's result was likely or not. Okay, so I'm going to make a table, null distribution. Call this null distribution. And put in my sample stats. Okay. Null. There we go. I can take that table and I can plot a histogram. So here we go. So what I've done here is I've plotted the histogram of my test statistic So I've taken one group of 929 plants, looked at how many of those are purple, compared it against 0.75, grew another 929 plants, count how many of those are purple, compared it against 0.75, another group. I did that 5,000 times. So I took a bunch of plants, and I plotted the results of those statistics right here. So here's the distribution. What this is saying to me, again, is that it looks like typical values fall between like 0 and maybe 0.35-ish, 0.3, 0.035, somewhere around here is what I can expect if Mendel's model was correct and I drew plants at random, or I grew plants and I got the results, right? So this is saying if Mendel's model was correct, these are typical values for my test statistic that I would expect to see. So I drew Mendel's actual result as a blue line here. And we can see that his result seems pretty likely to occur, right? So we say, oh, OK, it looks like Mendel's plants actually seem like they were drawn in a 3-to-1 ratio. So it seems like we have some evidence in favor of Mendel's result. Any questions about what I did? OK. So just like in the class, so in the classroom just now, I did like the weirdness example. What I did was I said, OK, how many guys are at least 10 weird, at least 50 weird, at least 85 weird? So my number was 85. I take my actual result, which is 85, compared it against you guys and said, how many guys got at least 85? And I used that to calculate the probability of me getting 85. In this case, I can actually take a look at this line. So this is the actual result. Mendel observed this. I can find the probability of Mendel getting his result or something more weird, right? Just like how in class, I can calculate the probability of me getting 85 weird or more weird. Yeah, question?
What is a good enough result to accept the...
Yeah, so what is a good enough result? That's a great question, and in fact, the topic of today's lecture. Okay, so what is good enough? Like if I move this line over, at what point do I say, oh, Mendel was wrong? It seems like it's not 3-to-1 anymore. And it turns out that what we want to do first is, well, sometimes what we can do is we can just look at the distribution, right? So if Mendel got a result that was like way out here, then we can probably immediately say no, like Mendel looks like he was wrong. If instead Mendel got something that was here, it looks like in this case, it's pretty clear that Mendel got a pretty typical result. What if the line was like here? So let's say I grew some plants. So I'm going to call this Sam tried again. And let's say I got a test statistic of 0.03. Okay. Plot that on my line. Sam tried again. There we go. Oh, Sam tried again. Okay. Let's say I grew some plants and I got this as my test statistic. Do I accept or do I like reject Mendel's hypothesis? Do I reject the hypothesis that it was 3-to-1, or do I fail to reject it? So that is a question that we're going to be talking about today. The idea is basically this, right? So the farther I go to the right, the less area there is to the right of this line, right? And that's because, remember when we talked about defining the test statistic, that we said the higher the test statistic is, the more weird my results are, or the more strange, the more deviation I get from my proposed proportion of 0.75. So the higher it is, the weirder it is, which means that I look at my line and everything higher than the result that I got. So I want to find the area of this right here. Okay, that tells me the probability of getting my result if my null hypothesis was true. Just like how when I calculated weirdness, I looked at anyone who got at least 85 weirdness and above. That tells me the probability of me getting 85, at least 85 in my result. Okay, so to find that area, we can just use the laws of histograms, which is basically to say the area here is the proportion of values that are above my line. Right? So I look at the proportion of values that are above my line. Since a histogram plots proportion in those areas, that also tells me the area. So I have here my results. Let's take a look at my sample stats. I have a bunch of statistics. Okay, and I can look at how many were above or equal to what I observed. So just to recap, what Mendel observed was this as a statistic. I'm going to look at everything that was equal to or above So I'm going to take that line and look at all the results that are at that line or above that line. Okay. I get a bunch of trues and falses. So again, I'm going to use np.count on 0 to find the proportion that were above my observed. So I'm going to do a len of my sample stats. And I see that about 55% of my results were above or equal to Mendel's result, which means that the chance that he drew his results, the chance that he grew pea plants and he actually got 705 of them out of 929 to appear purple, the chance of that happening we estimate to be about 0.55, which is pretty high. On the other hand, if I had taken my results, let's say I grew some pea plants, I got unlucky, and I got 0.03 as my statistic, the chance of me getting my results, if the null hypothesis were true, is only 0.03. So only a 3% chance of me getting my results. So it's a lot lower. Okay. This is actually a probability, like my estimation of a probability. Just like how in the weirdness example, I can estimate the probability of getting my results by looking at the proportion of people that got above 85 weirdness. In this case, I'm doing the exact same thing, looking at how many times my result got 0.03 or higher. That gives me a probability. Okay. That probability has a special name. It's called a p-value. So what we do when we conduct a hypothesis test is we have two hypotheses, right? One null, one alternative. And we say, OK, how do I choose between the two? I'm going to take my observed test statistic and look at whether it was likely to occur by chance if my null hypothesis were true. Okay? If I observe a value that does not look like it could happen by chance, then we reject the null hypothesis. And we say that hypothesis seems very unlikely given my data. That means that we leave, so only the alternative hypothesis is left. So the null hypothesis is, again, like a very narrow view of the world. It's saying, in this particular process, I drew the sample, and I happen to use like a very specific random chance law to select my sample out. The alternative is everything else. Okay, so the alternative is everything else. So in this case, I'm just striking out. I'm saying something else happened. I don't exactly know what happened, but something else happened. It was not random. It didn't look like it was random chance. On the other hand, if I get a result, and it does look like it can appear if my null hypothesis was true, then my test does not support the alternative. Okay, so the correct wording here is does not support the alternative, is not accept the null hypothesis, because it's not necessarily saying that the null hypothesis is true. It's merely saying, OK, if the null hypothesis was true, my result is likely. I don't know for sure whether it was actually drawn at random or not, but if it was drawn at random, then my result seems pretty likely. So that's the only direction it kind of goes in. You can't really say because I got this, then it was definitely a random process. I don't know if that can contribute to your result. So we can't say accept the null, but we can say does not support the alternative. Subtle wording difference there, but just note you either accept or does not support the alternative. Okay. Cool. Then I got a question of how do I determine whether I reject or fail to reject the null hypothesis? Sometimes just looking at the plot is enough, right? So we looked at the line, we're following the plot. We said, OK, sometimes I can just tell. Other times, it's not so hard to tell. I mean, it's not so easy to tell. So we use what we call the p-value, or another synonym for that is the observed significance level. It's just a fancy name to what we've already done. Okay, so it's a fancy name, fancy vocabulary, fancy words. But all it's really saying is, what is the probability of me getting my result if my null hypothesis was true? So if the p-plant ratio was actually 3:1, the probability of Mendel getting his result was 55%. The probability of me getting 0.03 as my result was only 3%, right? And that's assuming that the null hypothesis is true. We call that probability the p-value. The definition of the p-value is this long thing that says the p-value is a chance under the null hypothesis that the test statistic is equal to the value that was observed in data, or even further in the direction of alternative. And I already showed you how to calculate that. This is a long sentence that tries to be very precise about what we're calculating. But if you understand what I did with like the area and to the right of the histogram and all of that, then you understand what a p-value is and what it represents. Any questions about this? It concerns me that you have no questions, so let me ask you a question. What if I went back to my test statistic and I took out this absolute value, so no more absolute value, only parentheses? What would change? It's a hard question. I'll give you guys 3 minutes to talk about it. Go. Okay. Any opinions on what that did? How does my analysis change if I remove the absolute value? What do you think, Kevin?
Absolute value, you would have a bell curve.
I'll have a bell curve. Okay. So Kevin proposes that if I remove the absolute value, this will not look like a stairs. It will look like a kind of upward and then downward. Okay, that's fair. Any other opinions? If you guys are stumped, I suggest you go home and think about it some more. Let me run it. Show you what happens. Let's do that, do that, and do that. Okay, so it is indeed a bell curve. What does that mean? Let's compute my p-value one more time. So here I'm going to mark this as compute the p-value. Okay, so here it is before. I'm going to copy it. Here it is after 0.028. My p-value changed. My probability changed from 55% to 28%. What does that mean? Think about it tonight. If I'm feeling gracious, I'll give you the answer tomorrow. Okay, so let me keep going. Attendance. Go ahead and fill it out. And I will give you a hint for how to think about that question. So one key wording in the definition of p-value is in the direction of the alternative. Okay, so think about what that means. Think about what happens if I remove the absolute value. What am I comparing? What am I actually looking at if I remove the absolute value? Okay. Now, if you figure that out and you think you have a good handle on what that does, then you can remove the minus 0.75. Remove that. See what happens to your hypothesis test. Okay. But for now, I just remove the absolute value. See what happens. Okay. So again, the link here is bit.ly/@-d8. Those of you who did not see, I always like flip too fast, so here it is again. Okay. So we talked about p-value. We find a probability that my result happened. But where do we draw the line between rejecting the null and failing to reject the null? We just follow some conventions. Okay, so basically, somewhere along the line, someone said it was a good idea to set these as our cutoffs, and that's pretty much what the world has done. Okay, so we define inconsistent. If my test statistic is in the tail of my null distribution, which basically means, in the case of the p-plants, my distribution had like a slope that was going downward like this, right? I drew my line, so slope, drew my line. And if I go farther this way, then I get more into the tail of my distribution. That's really what that means. So in the tail of my null distribution, which means like at the very end of it, and we say, well, sometimes if the area of the tail is less than 5%, then we say, OK, that's inconsistent. We say the result is statistically significant. Okay, that's just a word we give to a result like that, which basically means the chance of me getting my result is very low, given my null is true. In the tail, sometimes we go farther. Sometimes we say, OK, we want the area to be less than 1%. Is also statistically significant, but instead we say highly statistically significant. It doesn't really have that much of a difference, because we just chose different values here, 5% or 1%. Okay. Generally speaking, you choose your cutoffs before you run your experiment, because otherwise you run into issues where like you can fudge your p-value cutoffs just to make your results look good. So typically, the correct thing to do is always choose it first, then run your experiment, run your hypothesis test, see what your p-value is, and then make a cutoff judgment from there. Okay. And where did these conventions come from? Well, came from this guy named Sir Ronald Fisher, who actually lived not too long ago. He said, very dramatically, we have the duty of formulating, summarizing, communicating decisions, blah, 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 blah. And other free minds utilize them in making their own decisions. So he was all for this idea of like, do some analysis, present your results, and then let your reader decide, let your viewers decide like which conclusion to draw. And he also said, it is convenient to take this 0.5% as a limit in judging whether a deviation is to be considered significant or not. So again, there's no like special mathematical or statistical reason why we chose 5%. He just said it was convenient, and so we were like, OK, sounds good. And we did that. So it turns out that 5% is the cutoff for most like academic journals or papers and stuff that you want to get published. Sometimes, like in some fields, that percent goes lower. So I believe in like health and medicine, they want that to be like 1% because it's more high risk. Some fields, like I believe psychology, allow that percent to go higher because it's hard to get very like definitive, clear-cut results. Usually speaking, 5% is the cutoff for p-values. Okay, so if my p-value is below 5%, I'm usually going to say, OK, it looks like my data is too inconsistent with my null for me to say that my null is true, so I'm going to reject the null. If it's above 5%, then I can say, OK, it looks like it's not weird enough for me to reject the null. I failed to reject the null. Any questions? OK, so he goes on to say, if 1 in 20 does not seem high enough, then we can draw a line at 150, 1 in 50 to 2%, or 1 in 100. So basically, it was just drawn arbitrarily. This guy just made it up, and well, it got popular. Okay, so there is an alternative way of looking at the p-value. Okay, so the one way is to look at it as a probability of getting my results given the null hypothesis. The other significance of the p-value, the other thing the p-value represents, is what we call an error probability. And what that means is sometimes my conclusion will be wrong, right? In fact, a lot of times it is. So here are the possibilities of wrongness. Okay, so let's say that I go back to my question about weirdness. Okay, so my weirdness was 85. I want to know whether I was drawn from the class or not. Okay, so in this case, the null is true, which means that I was drawn from the class, but I run my hypothesis test, and it does reject the null. So I look at the classroom, I say, OK, my my probability is too low, so I'm going to reject the null. But I did come from the classroom, right? So that's one mistake. I reject the null even though the null is true. That's bad. The other case is when the alternative is true, which means that I actually was not drawn from the classroom, but I failed to reject the null, meaning that I say that, oh, okay, it looks like I might have been from the classroom after all. Okay, so those are two types of mistakes. The p-value actually measures this mistake right here. Okay, so if my p-value is 5%, it also means that there's a 5% chance that the null was true, but I rejected it anyway. Okay, so two different interpretations of the p-value. Again, you want the p-value, lower the p-value is, the better it is, because that gives me a lower probability of making this type of mistake, which is rejecting the null when the null is true. Okay. So to formalize that, error probability, if my cutoff is 5% and the hypothesis happens to be true, but I don't know that, then there's about a 5% chance that I reject it anyway, which is problematic. That means that if my cutoff is at 5%, about 1 in 20 experiments, right, 1 in 20 hypothesis tests will be wrong, which is actually like not that low if you think about it. 1 in 20. And if you think about the number of studies people do all the time, 1 in 20 is actually, if you do like 100 studies, that's like 5 mistakes, 5 wrong conclusions, right? And so that's why typically in the scientific field nowadays, people are all about like being able to reproduce the study, lowering that chance of null hypothesis, lowering that chance that you think a result is significant when it actually is not. Cool. Any questions? Yeah, Luke?
Does alternative have to be the complement of null?
So Luke asked, does the alternative hypothesis have to be the complement of the null? The answer is yes. Because when I'm conducting a hypothesis test, it's like basically what I'm doing is I'm dividing the world into 2 possibilities, right? I'm dividing the world into the possibility number 1, which is that I drew my result and random chance gave me my sample. If I got unlucky, like if my result was different, it was just because I got unlucky. That's one possibility. And the other possibility to divide the world into 2 halves is just everything else. Anything else that could have happened, it was not random chance, but something else happened. Good question. Any other questions? All right. Well, close that. So let's see. Do I have anything else? No, I don't. Great. Think about this. Okay, so think about what happened when I did the absolute value and when I didn't. I'll see you guys tomorrow.
Hey, good question.